Thank you very much for allowing me to present. This is a great honor and privilege to be able to present to you today. Thank you very much to my colleagues for allowing this teleconference, or in the case of this video, backup video for the presentation, and for making accommodations for my family difficulties. And thank you very much for that. What I want to present to you today is we're going to go through an overview of a risk model, use of a Kuehl-Murray model, a quantitative microbial risk assessment model, and the redesign of a recreational site. This is not so much as getting to the regulations themselves or the policy in and of itself. However, what we were able to do was we were able to use Kuehl-Murray as a tool to be able to move forward what we could do by way of health protections for this recreational site. I'll also talk a little bit about how we have used Kuehl-Murray to develop some recommendations for regulation development in Argentina for peri-urban areas. We'll go over that at a moderate pace. And I'm going to finish on the slide with what I see a flow of what's going to be happening with Kuehl-Murray into the future, and really where we need to move the science in general, in my view, and especially how we want to try and hit those key policy and regulation pieces themselves. But first, what I want to do is really quickly go over a bit of a background on risk, where Kuehl-Murray came from, and how it kind of fits within the general sciences themselves and how it pulls from the general sciences. I like to consider risk as being one of those fundamental human concepts. If you put a seatbelt on when you get into a car, you've performed a risk assessment. If you decided not to have one more drink, you've had a risk assessment. Working at a university is a very important way of getting that kind of concept across of risk in general. And I like to pull it all the way back to really some of the first quantitative thoughts we had as a species. So if you think back to the caveman days, there was somebody, one person, who came up with the idea of hunting a saber-toothed tiger or a mammoth. And probably conversations went something like this. You know, we should probably hunt that big thing over there. I bet it's got a lot of meat on it. Yeah, but have you seen how big that thing is? It's massive. Yeah, there's a lot of meat, but it's going to crush us. But think, we won't have to hunt all these other dangerous animals if we get that one thing. All winter long, we'll be fine. So somebody won at some point, we hunted the mammoth, and we continued as a species moving forward. Taking different risks means that you have to quantify in some way what that risk is going to be to you, or else there's a possibility you won't survive that risk-taking endeavor. If we think back to ancient Rome and even ancient Egypt, we actually had groups that were in charge of risk assessments. There was a tribe in ancient Egypt that was the go-to for the pharaohs when they wanted to build a large infrastructure project. How many slaves were going to be killed in the process? How much money is this going to cost? What are the supplies we need? Things like that. One-stop shop for people to be able to get some kind of risk model out of it. Not in the same kind of context of risk model that we talk about these days, but back then it was very important. Ancient Rome used to have an entire contingent of soldiers and scientists, not really called scientists at that time, to catalog all the poisonous plants in the empire. And if you think about how big the Roman Empire got, you can get an idea of how much work this really entailed. So we fast forward a little bit into the medieval period, and risk really gets its first definition as a word, risicum, where we want to understand what are the losses that we're likely to incur by having these large ships go across the ocean to unknown locations, and locations where we're going to have to fight to our ability to colonize those areas. That's where we started really getting an idea of quantifying it at a financial basis, and that's really where it started at that point. But what we're interested mostly is microbial risk assessment. And where microbial risk assessment started is really it started to bump off from chemical and radiological risk assessments. So during the Cold War, we have a big boom, no pun intended, in the risk fields themselves. What are the overall losses that we could expect to incur? Are these acceptable losses? How do we mitigate these different losses that could end up impacting us? When we're talking about chemical risk assessment, that's where we're starting to look at thresholds, looking at TOEFLs and other no-effect levels to try and assess where a safe spot is for us to be able to move forward in whatever decisions it is that we're going to be making. The NRC, or National Research Council handbook, that you see the red image, the red book in the image, is really where we started setting down guidelines on what we should be doing when we want to build out a health-based risk assessment. And realistically, that's about when we started pulling out more officially what Cuillermoret is. But the genesis of Cuillermoret, I like to point back to about 1982, Dr. Charles Hawes developing the first mechanistic dose-response model for microbial risk assessment. This is really what made QMRA quantitative. Instead of it being a qualitative or trying to use threshold approaches that really don't work in a Cuillermoret model, you can now have a quantitative risk estimate as an output because you have these mechanistic dose-response models. It was a big boom to the science in general, and it really started moving it forward. And after that, we started putting in more and more knowledge and understanding. We started finding more and more research gaps, knowledge gaps, data gaps. And we have to start filling those as we move forward. One of the pieces was how useful is QMRA in a realistic scenario, and that's what we're going to talk about with the Cryptosporidium Spray Park. The name of the spray park is not something that I advertise around because it was a private company that we were working with, but for lack of a better term, we call it the Crypto Spray Park because there was a big problem. What ended up happening was, and I won't go through all the bullets on here, but you can read them if you wish. What ended up happening was there was a fairly substantial outbreak at a recreational spray park in Lake Seneca in upstate New York. So there's New York City, the islands on the right-hand, the east coast of America, and then there's the state itself that those cities are a portion of. Upstate New York is in that larger portion of the state itself. And it's a really nice area for recreation. There's some very nice lakes and very nice natural areas. But one of the issues with recreating in the natural environment is if you have small children, you may not want them to go out into the lake and then risk drowning or being pulled away from the current, because some of these lakes are called finger lakes. They're very long lakes, kind of like the Lake District in Italy as well. We have these long lakes, and they get some very interesting current patterns that can be dangerous to smaller children. So they have recreational spray pads where essentially that's exactly what it sounds like. You have devices that are going to be spraying water. So you have a pad where you're going to do most of your recreation on, and then you'll have these look like flowers, and they'll spray water down onto the recreating children. And of course, children being children, they're going to be recreating around, dancing around with their mouths open, filling their mouths up and everything else. So any kind of treatment that's not happening or is less than efficient in this spray pad area is going to be exacerbated by the children's recreational patterns. So what we ended up wanting to find out was what was the actual risk that we were going to be seeing to the children based on the what we knew from the outbreak itself. So what we could be able to tell from the outbreak itself was an ability to figure out what was the overall attack rate to the community, and we could do some epidemiological work. And if we can do that epidemiological work, we can back calculate out what a likely dose was going to be. So we set up a case control study, and the case control study was really the best we could do. We couldn't do a randomized control trial because it's a disease outbreak. We don't want to try and replicate something like this. And a cohort study was going to be a little difficult as well to be able to try for. So a case control study was as good as we could get on the epidemiology. And this is an engineer speaking to you about epidemiology. So if there's epidemiologists in the room, I apologize greatly for misclassifying certain practices within your field. But that's one of the risks that we take, pun intended in that case, when engineers do a lot of the Cuillermoret work. So we can see basically the case control study as it broke out. We had a large number of subjects that we were able to draw in. Some of the subjects we had to just not use because there was no ability for them to track how often they had gone to the spray pad, if they had been there specifically within the outbreak period, and whether or not they had other co-exposures that could have been more likely that was the cause of their cryptosporidiosis. But all those cases, all those initial subjects were cryptosporidiosis cases in that general area around Lake Seneca in New York, or people who had traveled there, recreated, and then went home. So what we were able to do is we were able to try and back calculate out what a likely dose was that people are exposed to. Remember, what we're talking about is primarily children in this case. There aren't really very many adults that are going into these spray pads. It's more of a cultural issue where the children are recreating on their own and parents don't typically go in and recreate with them. If the parents are going in, they're probably, or grandparents, they're probably going in to rescue a child from having fallen over or a fight broke out or something like that, but they're not really recreating in these areas. So we were able to back calculate out a fairly low dose, really, when we think about it. And there's some assumptions in here where we had to use a shedding rate that we assumed was constant for a child population, even though the data itself isn't from a child. So that kind of gives us an idea of some of what we can do with the QM array. We were able to take what we saw by way of exposures and run that through a dose response model to solve for a dose to give us an idea of what the contamination level actually was. And so what we ended up seeing here was we went from a characterized risk, or the second to bottom box in the flowchart here, up through the dose response model itself to figure out what that exposure probably was, because we knew what the hazard was. We knew it was cryptosporidiosis. But in general, the QM array framework is very easy to be able to manipulate, to be able to solve a number of different problems. You don't have to start from, I am concerned about cryptosporidium, and then go through. You can start from, I want to reduce the issues of cryptosporidiosis. I want to reduce the issues of severe gastrointestinal disease in general. And then you have a whole suite of pathogens that you would have to model through. Where we use this a lot in my beginning stages was in bioterrorism issues. So we started with what are the likely agents of bioterrorism, and then we would move through as we went through the paradigm itself. But as you can see with the flowchart, we have some of these back channels coming up. So once you've characterized and managed your risk, is your risk managed to an acceptable level? If it's not, where in the exposure or dose response is it going to be much more likely for you to be able to get that answer? But back to the actual spray park itself, what we ended up deciding was we could have stopped at the dose and said this is what you were exposed to. Probably what happened was the child had a fecal event on the spray pad, didn't get caught, went into the system, and now you have a problem. And then left it at that. We could have left it at that, but it didn't make any sense. Ethically, it really didn't make any sense for us to just leave it there because there's still people at risk at that point, and we know it. So we need to do something about it. So what we did was we modeled the actual system itself, and this is a flow diagram of the system, obviously not to scale or to actual shape of what it is, but you're recreating on the spray pad and you go through the treatment itself. If you look at that second tank, so you have tank 1 where you have a chlorine reaction happening to kill off the E. coli and indicators that they're monitoring for, because that's what this was designed for, then it comes back to tank 2 and then it goes back out to the spray pad. So if there's engineers in the room, obviously what you're going to think is, well, you got a pipe coming in and out of the same tank where you have dirty water coming in and clean water, theoretically clean water, coming back out. So what ended up happening was we called this the bypass pipe. So that little pipe that goes from tank 2 back to the spray pad, and of course the pipe that goes from tank 3 to, from the reaction tank to tank 2, sorry, from tank 2 to tank 1, is basically what we ended up calling the bypass pipe, because you're realistically bypassing your treatment overall. So we went through and we decided, what do we want to know? We already were able to back calculate out what a likely concentration or likely dose of oocysts were for the cryptosporidium. Now what we want to do is we want to try and figure out what can we do to stop this from happening in the future. The whole point of QM array is to try and beat the epi curve. And again, any epidemiologist in the room, I apologize if that offends you, but epidemiology has a context within it where a disease event occurs, and we now try and figure out what happened and try and stop that from happening in the future. QM array is trying to prevent the disease incident from occurring in the first place. We're trying to predict and project out what a likely risk is, or what a likely set of health effects are going to be based on a specific set of constraints and initial conditions to whatever the system is. So if it's drinking water, we want to prevent a cryptosporidium outbreak in the drinking water system. If it's a bioterrorism type of model, we're trying to prevent mass death from a bioterrorism incident, and then we move forward from there. So we're trying to make sure that nobody returns onto that epi curve and shows up as portion of an outbreak again. So that's what we're really trying to do. We're trying to project out and say, what is it that we can do to try and mitigate this from happening in the future? And to do that, we need a little bit of knowledge on systems modeling or process modeling as well. So I'm showing you a box model. A box model is a very simple way of modeling a physical system. We're not going to go through the gory details of everything that happens within the box model, but I'll show you some of the math that goes into it so you can kind of see the beautiful simplicity of a model like this that can still have accurate, high-resolution, quantitative power to it within a risk model overall. But we have things coming in and things going out. That's basically what it is. Q and C. Q would be a flow rate in, so mass flow, or a volumetric flow of air or water. And then C would be a concentration of something that we care about happening. And there's a volume, so V with a line through it is engineering shorthand for volume. And we need to know what's going on in this control system itself. Whatever's happening in this box we care about, we want to make sure we understand everything that's going on. And a Markov chain is a perfect way of doing this. Again, for simplicity. We did not have a ton of time. We did not have a lot of resources to be able to accomplish this. There are more sophisticated ways of modeling a drinking water system, which this is somewhat analogous to for how it was operating. However, for overall resolution of what you're trying to predict and to try and assess the uncertainty of the situation at the same time, a Markov chain or some other stochastic system is an ideal way of doing it. In this case, what we did was we modeled the treatment systems at the recreational spray park using Markov chains, and then we inserted the values from the results of those Markov chains as distributions into a Monte Carlo and modeled the risk in a Monte Carlo. We'll talk about that in a little bit. I'm only showing you 3 of the design changes that we implemented. They're actually only showing you 2 of the design changes because one of them is the current configuration, or the original configuration. So the original configuration you see there with the bypass pipe in place. The first change that we made was we just removed the bypass pipe and kept everything else the same. And then we put in an ozonator. We also did some other ones where we put in a UV system. Instead of an ozonator, a UV, then an ozone system. Changed where, in which position the UV and ozone was. Do we ozonate or UV before we put it through chlorination? Do we do it after chlorination? Do we do it before filtration, which engineering-wise doesn't make much sense? But we tried in a number of different configurations because at this point as well, I wanted to see if we could trick the model into giving us really bad results, and we really weren't able to. To construct these things properly, they're very robust. And here's where we start seeing the simplicity of this type of modeling. We see the overall simplicity of being able to say, we have a flow coming in and a concentration of contaminants coming in, and we need to be able to assess how they're moving through the system, and we also have to be able to assess how we're removing them. So we have a log reduction credit that we're putting into that bottom equation that will allow for some level of treatment of the cryptosporidium. Obviously, chlorine's not doing anything. They have a filter and chlorine injection, and that's about it originally at this site. But we gave them a relatively good log credit for cryptosporidium removal because they did maintain their filters properly. There was a good switch stack in place on those filters, and so they were operating them very well. So, but what you can see is the overall raw simplicity of it, because once we have those loss rates, once we know physically what's happening to the oocysts as they're moving through the systems, they're being transported, and then as they're being removed via filtration or just their natural die-off, we can place them into a survival probability for our top equation, which is telling us whether or not it's going to stay in the same state that it originally started in. So let's say I cough into the air, and I have pathogens come out into the air. Now I have these pathogens out here. Let's say that we want to model what's going to happen to these pathogens. They can either deposit, or they can go onto a surface, or I can respire them back in, or there's a number of other things that can happen to them. They can also die in the process. State I would be the air. There's a probability that they're going to stay in state I, and if you look at how these equations are written out, you're given an overall bias to them staying in the state that they're in because the time scale that you're modeling these at is very, very small. You're talking about the second or millisecond or nanosecond or picosecond scale depending on how fine of a resolution that you want for your model. And so obviously we're going to give some level of bias that they're going to stay in the state that they were originally in to begin with. So if it's a coughing scenario, it would be them staying in the air. In this case, the oocysts stay alive in the bulk water, and that's basically where they are at that point. Then we have a probability of being in one state, so being in the air, and then being in another state or depositing to the floor. And so what we're doing there is we're saying we have to account for whether or not they're going to stay here, and then we have to account for the losses that will allow them to settle out and deposit on the floor within each of these time steps. And again, these are very fine time steps that we're typically working in. This is one of the reasons why a Markov chain, even though it's really very simple, to be able to build out, and very quick to build out as well, is still going to be very accurate and have high resolution if you build it properly. So once we've gone through all the Markov models, what we were able to do is put them into a Monte Carlo. The distribution and results were fit to probability distributions and used in a Monte Carlo model. Set the seed at, I think, 36 when we were running this, and then we're able to start simulating what the risks were. Now what we ended up seeing was there was always this large risk, and there was always this small risk. You were always bounded on either side by your extremes. And this is because what we were simulating was an incidental fecal event. So what happened was we were simulating a child would be recreating on the spray pad, and then they had an accident. They pooped on the spray pad, and we had a host of oocysts. So we allowed that to range from between 10 and about 200,000 oocysts in the feces that was dropped out. And then we basically said in the model that nobody caught it and it went back into the system, essentially replicating what happened in the outbreak itself, or what we surmised was able to happen in the outbreak itself. And this is what you end up seeing. You end up seeing very high risks, but as you change your treatment, the probability of those risks is going down. And that's the important thing. What we're trying to say is we're trying to predict out what's the probability of this health impact from occurring. What that allowed us to do is that allowed us to say, this is the overall benefit of these design changes based on a predicted health risk. That then gets tied with whatever financial impacts as well. This is a business that we were working with. Their easiest way of reducing risk was to just shut down. That was the absolute easiest way for them to be able to reduce risk, but they provided the service to the community, they were making money, they didn't want to end either of those two things. And so what they ended up doing was they ended up going with a specific design change recommendation. We haven't heard anything since. Again, I can't really talk about what the design change was or where this is, but it's really important to note that what we were showing them was there's still going to be a risk. There's always a risk of some health impact. But what we can do is we can reduce the probability of that risk from occurring and therefore save people time and their lives and their health at the same time. So you can mold that into whatever the financial impacts are and then make your decision based on that information as well. But until you understand what that probability of risk is really going to be, it's going to be limited in what you can do, and you're really just making a financial judgment at that point. So I don't have a ton more time to be able to talk, but what I want to do is talk a little bit about some developing nation, peri-urban area regulation work that we've been looking at. And this is really fairly new. Where we're advancing it now is looking at helminths and internalized cysts within helminths as well, because they have quite a problem with that in this area as well. But we can give you the overall broad strokes of what was occurring. So in Argentina, one of the problems that we ended up having, and let me move here, sorry about that. So in Argentina, one of the problems that we have is that the regulations have not really kept up with what the drinking water quality can be. So to reach the Millennium Development Goals, which have now obviously been replaced by Sustainable Development Goals, but during that time, during the Millennium Development Goals, they were putting in a lot of different water treatment and sanitation treatment options that were either working or not working. There wasn't really a very easy way of assessing that. And so the regulations really didn't catch up. They don't have any protozoa regulations at all. They're really just looking at indicators, E. coli 157H7 and Pseudomonas aeruginosa. Those are really the only pathogens that we're looking at when we're talking about Argentine drinking water regulations. And so what that ends up happening is design, engineering design, always follows regulations and costs. You cannot have endless money to be able to build whatever it is that you want to build. We have the best intentions in the world as environmental engineers, but we are constrained by both the costs and the regulations, and the regulations are typically built around both risk reduction and cost. And so where Argentina was a little off in their regulation development was they weren't really looking at the overall risks to the population, and that was blatantly clear by not having a protozoa regulation. So what we see here is some of the data that we have in box plot format, and so you can see that Giardia is a problem overall, and they're achieving pretty good overall reductions. This is a peri-urban area, very poor area, and so some of the water sources that they have are either completely untreated or quote-unquote treated, meaning the water treatment agency will put chlorine in the boreholes, which obviously is causing a whole host of other problems, such as disinfection byproducts probably. but also is doing absolutely nothing to the cysts that are in the system as well. So what we wanted to do is we wanted to go through and say, can we model the risks to be able to inform the Argentine government in some way of what the overall risks are? And what we ended up showing was there is obviously a problem here by way of the overall water sources themselves, and especially for Giardia. Nothing's really removing Giardia. These are the basically uncontrolled or less controlled sources than the drinking water plants that they have. In the next slide, we'll see the drinking water plants. Sorry, that only serves about 15% of the population. So what we're seeing in these risk estimates overall is that they're really not doing a very good job in Pseudomonas. They're doing a great job on E. coli overall, but not great in some of the untreated areas themselves. And then Giardia is pretty much just off the map on overall risks. And it's again because this is a very aggressive pathogen we're talking about. The treatment plants themselves are obviously still having a problem. E. coli, great. Pseudomonas, they're doing pretty well on that. Giardia is still having a pretty large problem overall. Now, what does this tell us that we can go and say to the government in the future? Now, we haven't really approached the government yet at this point. What we want to do is we want to build out a water safety plan, make the QMRA communicate with the water safety plan to be able to make that as appropriate and accurate as possible for the water safety plan. And we want to look at some of these other pathogens as well. There are internalized cysts within helminths, so the worm will eat the cyst, then you will ingest the worm will die in your system because it's a non-pathogenic worm, and then you'll have live protozoa in your gastrointestinal system as well. It's kind of a biological delivery mechanism of sorts for cysts. So that's the next piece that we're looking at now. Then we want to put into a water safety plan. So there's a lot that we have to do before we can get this to the Argentine government. But initially what we could do is we could go and say, you're obviously not doing enough about Giardia, but of course in a much more respectable way. So one of the things that we need to understand when we're presenting this kind of information to government decision makers, regulators, and other decision makers overall is that there are realms of reality that we need to live within. And we'll see as well where we have to go with QMRA to become more accurate as well. But we have to understand that we live within these realms of reality. There is not endless money. There's not endless political capital. We have to be able to understand that priorities have to be made, they have to be met, targets have to be achieved, and there has to be money available to do any of this work in the first place. And so that's one of the reasons why I'm a very large proponent of QMRA as a science becoming a much more open source and freely distributed science in general. If you're spending a lot of money contracting someone like me to come in with my consulting firm and perform a QMRA model for the amount that we're probably going to be charging you, you could use that money within more sampling to develop more, better data to have a more accurate QMRA model. But what we can see with this overall flow of the science in general, we can see where we came from and kind of where we're going at the same time. So we've made our way through, we've developed the dose response models, well, Charles Haas developed the dose response models, and then CAMRA, the Center for Advancing Microbial Risk Assessment, was an explosion of QMRA research. Absolutely fantastic time to be a QMRA researcher because you were able to expand the knowledge and the data to amazing realms. Then as we moved forward, what we realized was there's a difference between a Monte Carlo, a standard Monte Carlo, and a two-dimensional simulation. Do I need to assume everything is uncertain, or can I say some things are variable, some things are uncertain, and then look more heavily at the uncertain parameters and variables within a model? It gives you that extra level of accuracy. They are harder to build. They take longer to run. They are more memory intensive. And so computationally, it is not something that you just dip into just because you want to run one. You need to be able to have the justification for why you're running it, and you need to understand how you're running it. And that's where we started to make a bend. We started to realize that not all stochastic methods are created equal, and we need to start being able to adapt what we're doing to what needs to be done for the model itself. And then where we see the mouth of the river overall, I see it as trying to understand some of these next level questions. Detection limits are a big problem within environmental data. If it's below the detection limit, it does not mean it's zero. It just means it's such a low concentration we weren't able to see it. But if we assume it's all zero, we're skewing our risk too far to the low end without knowing whether or not it actually is that way. If we say it is equal to the detection limit, we're skewing our risk assessment to the high end that little bit more. And again, now we might be costing ourselves more money, more time, and more resources than we actually need to dedicate to this. So there's somewhere in the middle, and realistically, let the data speak. The data are what they are. We need to allow them to be able to say what is happening in this water system, and that's where we see the split distributional approach, or using of joint distributions for detection limits. Well, we need to agree. We need to be able to find out whether or not this is the absolute best approach to move forward with. Social dynamics, understanding behavioral aspects into QMRA. We typically just take that, plug it in at the risk management point for the communication and risk perception strategies, and then say our job is done. And it's not really the case. How people recreate, how people drink, how much stress they are under affects their respiration rate if we're talking about an inhalational pathogen. All of these things are either stress or behaviorally mitigated as well. We really need to understand those and incorporate them into a QMRA for the science to move forward. And we have a number of other forefront issues, but have already been long for right now. If you want to be able to email me, Tora will be able to give you my email address, and I can also be available for phone conversations or via Skype at the same time. Again, thank you very much for having me. Thank you very much for accommodating me via this video as a backup for the case the teleconference doesn't work. It has been a great pleasure presenting to you. Thank you very much.